Okay, so this video is going to talk about what to do at each vertex of the traveling salesperson problem. We're not going to go through a whole example. Instead, we're just going to look at if you're currently sitting at one of the vertices in the decision tree attached to the traveling salesman problem, what do you do with your cost matrix at that specific moment in time? Okay, so right here is a list of what you would do. So when you're looking in your cost matrix, you're currently on some selected row, and let's go ahead and call that row I because, well, it'll change out depending on where you're located in your problem. Okay, there's two possibilities. When you look at your row I, you'll scan through the row and you'll look for all your zeros. Maybe you have exactly one, maybe you have more than one, and you choose one of those entries in the row to select. Okay. Case one is where you actually select the zero. If you have more than one zero, it doesn't matter which one you select, you just pick one of them. And then the other option that you're going to have, so this is the two children of the current vertex you have. The other one will be where you didn't select the entry that was a zero in the row. Okay. Now, if you do select the entry, you adjust the cost matrix so that you're never going to actually not get a Hamilton circuit. In other words, you're adjusting it so that you don't accidentally close off your Hamilton circuit too quickly. In other words, build sub-circuits along the way. So first thing that you would do is you're going to go ahead and take the row and the column that your zero entry that you selected is in, so that row I and then the column J, and you're going to turn all of them into infinities. And remember, we said previously that infinities were our way of saying we're never going to go back and use that entry again. You can also go ahead and just cross off the row and column, which is actually what we're going to do when I go through the little example here in a second. Is I'm just going to put a line through that row and that column. Now, the other thing that you want to do is you want to make sure that the next step is not going to close off your circuit too quickly. So as long as this isn't the second to last step, you go ahead and you say, hey, the jth row, so notice where our zero entry came from, our jth row first column is going to be set equal to infinity. So this means we're not going to close off our circuit too soon. Okay. We'll recalculate our lower bound. So remember, this is where you scan through each row and each column, make sure that there's a zero in each case. If not, you adjust. Okay. And then our new selected row in the next iteration down, in other words, the children of the vertex we're building right here, is going to be based on now row J. Notice where the J came from. Okay, so we'll go through an example to show you how to deal with all of those individual details. And this here is you just iterate and do this at every single vertex you can until you can't do it anymore. Now, the sibling of that vertex that we would build is where you don't choose the entry that equaled zero that you selected before. And in this case, there's really only two things to do, and it's a lot less work. First of all, the entry that you didn't choose, you set it equal to infinity to say, hey, that's an entry that we didn't choose, and then you recalculate your lower bound. So notice there's really not a lot of work here. And in fact, there's exactly no work here if the row I or the column J have more than one zero in them. There wouldn't be a recalculation of your lower bound. Okay. However, in many cases, there's exactly one zero, so you'd have to recalculate at least one or two numbers. So let us look at an example next. All right, so this is the example we're going to go ahead and look over. It's actually from our textbook question number 5 if you want to look it up on your own. So this example here is just a 5x5 cost matrix. So in terms of what you could think about this as, you could think of this as your traveling salesperson traveling across 5 different cities. Okay, so first thing that we're going to do is we would calculate our lower bound, and if this was one of the prior vertices in your decision matrix, you would already have your lower bound. So let's go ahead and grab our lower bound right here. So we'll scan across every single row, every single column, and find our smallest entry. So I went ahead and circled our smallest entries here. Notice in row 2 we actually had multiple choices, but at the end of the day we're just going to subtract your smallest entry from each row. So which entry is the smallest doesn't really matter. 2 entries both being tied for your smallest value just means you're going to have more than one zero. So we'll go ahead and subtract all of these guys and create our new matrix that we're actually going to start from. So we go ahead and we subtracted the smallest numbers from each row, and then we check to make sure we have zeros in all of the columns as well as all the rows. And as we notice here, we don't. In the last two columns, we don't have zeros, so we'll go ahead and we'll adjust. And notice in both of them, the smallest number is 1, so maybe we think of this in terms of this guy, maybe this guy. Okay, so we'll go ahead and we'll subtract 1 from each of the last two columns and add that over here to the side to get our lowest bound, or lower bound, I should say. So we go ahead and we've subtracted 1 from the last two columns, went ahead and added up all of the numbers that we adjusted our matrix by, and we got a grand total of 12 right here. Now at this point, we're at the starting point where we would be every time we take a vertex in our decision tree and we look to see what's going on with each of its two potential children. Now, since in this particular example, I haven't done any previous work other than the very first starting point, this is technically speaking the root of the decision tree for this particular example. However, again, if this was some middle vertex in the middle of your decision tree, all of the work would be exactly the same. We just wouldn't be starting at row 1. Okay, you always start at row 1 by default. So in our case, in terms of what we're going to be doing, our selected row is here row 1. So this is where I equals 1. Okay. Now you have two options. Option number 1, or case 1 here, is where you choose your 0 on your row. That's always the one that you want to do first. So here I'm going to be lazy and I'm going to go ahead and select the 0. That's the first 0 right here. We also could have selected the 0 that's over here on the far side as well, and that's totally fine. Now, once we've selected that first 0, here's what you do. Okay, I would recommend always giving yourself a little bit of a game plan of what you just did. So here I say, hey, in our cost matrix, we selected entry 1, 3. And what did that also allow us to do? Because we're in row 1, we're moving from city 1, and now we're moving to city 3. We don't know what's going up next, but we always know this. Notice the subscripts match exactly your entry and your cost matrix. Now, once you've done that, I'd recommend copying this matrix exactly as it currently is in the new child node, or the child vertex. Okay, so I've copied the matrix down exactly, highlighted the entry that we've selected that gave us this particular branch, this edge coming down to our new vertex. So first thing that you want to do is you want to go ahead and get rid of the row in the column that this entry lives in. So I'm just going to go ahead and cross this off with a single line. Technically speaking, all of those should transform into infinities, although some books just go ahead and actually physically delete the row or the column and shrink the size of the matrix. It's personal preference. I have found that most people do best dealing with this right here. Okay, so that's the second thing, the first thing to do with the new matrix. Second thing you do is you go and you find what would close off the subcircuit. So specifically, if in the next iteration that we would do, we would travel from city 3 back to city 1. We don't want to do that. So city 3 to city 1 would be this entry right here. That guy currently has a cost of 2, but we want to make sure we never choose it, so we're going to bump that cost over to infinity. So I'm going to go ahead and just change that 2 to an infinity. The last step in this building this child node, this child vertex right here, is now to go ahead and recalculate your lower bound. Now remember what you have to do to recalculate your lower bound. You have to have a 0 in every row and in every column. So row, 0, 0. We don't have a 0 here, a 0 there. So we are going to have to worry about our smallest number. So our smallest number right here is a 2. So we're going to decrease that guy by a 2. Now, quick check. Let's see if there's a 0 in every column. 0, 0, 0, 0, and that's not going to be changed when we affect this row. So the only entries that we're going to change up are this row right here, and we're going to go ahead and adjust all of those guys by decreasing by 2. Which then yields us this row right here of the 0, 2, infinity 2. Note the infinity doesn't change because you subtract 2 from infinity, it's still infinity. Now, this then adjusts your lower bound. So our lower bound used to be 12. We adjusted by 2. So this means we have 12 plus 2 or 14 now for our new lower bound. Okay? So here's our original vertex that we were dealing with, and one of its children would be this guy. Key things you have to keep track of. You have to keep track of your matrices, and you have to keep track of your lower bounds. Some people find it helpful to do 2 copies of the matrix inside of the vertex, one the scribbled up version and one the cleaned up version where there's no scribbles on it anymore. Okay. Now, if you wanted to then progress to the child of the vertex we just built, you would repeat this exact same process. This would have 2 children. One of them would be, you'd now be focusing on row 3. And you'd select one of the zeros from row 3, doesn't matter which one, and that would be this leftmost branch, mimicking exactly what we did right here. Now, there's always 2 branches, so the second branch that we had deals with what happens if you don't select that entry 1, 3. Well, if you don't select the entry 1, 3, this is where you don't use the entry 1, 3. This is where you set that entry 1, 3 equal to infinity. Everything else is exactly the same. So let me copy down this exact matrix with everything except for that one entry point. Alright, so we've got the entire parent matrix down here, or the matrix of the parent vertex is copied down, except for this one location. So let's go ahead and highlight that one entry point right here. Now, since we're not allowed to use that guy, the only change we're going to make over here to this matrix right now is to convert that one entry point into an infinity. Now, the second thing you have to do, and this is you have to do in either of these 2 children vertices, is you do have to recalculate your matrix by way of figuring out the lower bound. Okay, so how do we do that? You always check to see if you have a 0 in every row and every column. So first row, we still have a 0 because there were 2 originally. Still have a 0, still have a 0. We're checking rows, still have a 0, still have a 0. So all the rows still have zeros. Column has a 0, column has a 0, column has a 0, column has a 0, column has a 0. So there's no adjustments here because we still have a 0 in every row and every column. And for this particular matrix, there's a lot of zeros originally, so there's probably not going to be too much adjustments with respect to your lower bounds. What that means is if there was no adjustments, you didn't have to subtract off by any smallest numbers for your missing zeros, your lower bound here matches exactly the lower bound from the parent matrix. Okay, from the matrix in the parent vertex. At this case, you then look at these 2 guys, you say, all right, well, who has the lower of the 2 the lowest of the 2 lower bounds, and then you start looking at, all right, well, where do I need to go next, etc. But when you are at each vertex, this is the exact procedure right here of saying, hey, which of these 2 guys am I going to deal with? Notice of the 2 lower bounds in this particular case, the lower one is the one that says we don't use entry 1, 3. What that tells me is instead of picking this 0 right here at position 1, 3, the one that we actually need to do is the one here at position 1, 5 would be the one that actually gives you the lowest lower bound at this point. Okay. But that's the idea in terms of what you do at each row, and to figure out what the new row is that you're dealing with, notice right here, it is the position or the column that the entry is you selected from the previous step. So here, when you move forward, you're going to be looking at this row 3, so you'll be selecting here a 0 from row 3 if you continued on down and dealing with that matrix.